And when Henry Ford, one of his famous sayings is that if he asked his customers what do they want, they would say they want faster horses.
Ladies and gentlemen, please help me welcome the Innovations Director at Gendermark, Yanesh Naidu.
That intro applies no pressure on me. Thank you. One of the biggest challenges we have, sorry, the picture's a bit cut off, but basically that's Henry Ford looking at a horse and carriage. And when Henry Ford, one of his famous sayings is that if he asked his customers what do they want, they would say they want faster horses because they can only imagine horses. And so if you go to a factory, a plant head or an engineer on the shop floor and you say, what do I want? They only answer questions in the context that they have. They want faster horses on their shop floor. But he invented the car, and that's a complete paradigm shift. So how do you get factories to change? Because factories are difficult and they're physical things to change the paradigm of a factory. And I think that's extremely difficult, and that's part of the challenge. If you walk around this room today, there's certainly no shortage of technology. The technology exists. It is the adoption and how you change people's minds on how to use the technology is actually the barrier that we face today. So, as I mentioned, today's talk is quite technical. I'm going to be focusing on AI because obviously this is a transformative topic, and I'll be sharing with you real-life examples of how AI has been transforming mindsets on the shop floor to help maybe potentially spark your process as you go through this journey in your environment. I'll be dividing it up into three sections. The first one is computer vision, second one is digital manufacturing, and the third one is, and I'll breeze through the last one quite quickly because everyone talks about large language models and chatbots, so I'm going to kind of get through that quite quickly, and then I've got a fourth one that I'll talk about towards the end. The reason why there's all this text is because I'll put the presentations online. I've got a QR code at the end that you can download and actually get the presentations, and I'm filming myself, and there'll be a video of this whole thing on YouTube if you're interested. Selfish plug for my socials. So I'm going to start off with computer vision. So computer vision is a very simple concept. It's basically the same process that we have with our brain. We have an eye that can see a bowl of fruit. The brain processes that based on your years and years of learning about different kinds of fruits, and then it outputs what is in the bowl. As a kid, that's what you kind of go through. You learn that this is an apple, this is an orange, and that's exactly what machine learning from a computer vision perspective is from a technology perspective. So this is a technology version of exactly that. You have a camera, some computer system, think of that as the brain, and you can teach this computer system to read the images from the camera and teach it to say that there's apples, oranges, bananas, etc. And that's ultimately what computer vision is trying to do. And when we talk about these fancy terms about machine learning and models and algorithms, all we're doing is we're writing some software in the computer to recognize and classify what those objects are. So how do we use this in a factory? So let's talk about one kind of computer vision. The first one is called classification. So classification is very simple conceptually. So this is an example of three different types of rims. And so what we can do is we can input thousands of images of those three types of rims and can call them type 1, type 2, type 3. That's what we call labeling the image. So we can say image 1, image 2, oh, type 1, type 2, type 3. We can put this into the fancy algorithm, and I put this here to make myself look clever. I actually don't know what's going on in there, but the computers do all of that stuff. And out of that, we can then create this model. And so then if I give it now an image it's not seen before, it'll recognize that that is actually type 1. And if I put the type 2 rim in, it'll recognize that that's actually type 2. So how do we use that in a factory? So today, it's the biggest use case is actually picking of components inside a factory. So you have these classification models. So you have a whole bunch of rims. Is your new BMW X5 coming down the line that you've ordered with the 25-inch rims with low-profile tires. The robot needs to know which rim to go and pick to go and fit onto your BMW X5. So you can use a classification model to select which rim needs to go into your particular car. The algorithm can do that, and then you pick the right rim. Today, what happens is a human goes there and says, okay, this is the rim type, because they can recognize that. Maybe put that into a machine that then gets automatically put in there, but now we can kind of close the loop in that picking process. Here's a real example, just sticking with the BMW theme. So this is a video from BMW in Roslyn, a supplier to BMW in Roslyn. So these are the X3 axles. And what we've done is we've created a classification model to determine the orientation of this, what we call a pellet. So this is the axle, and we assemble the axle on our big production lines on what we call a pellet. And what's very important is that we need to know left and right, because if I'm tightening on the left-hand bolt, I need to know the axle is in a certain orientation, so I tighten the right bolt. So you always need to know the orientation of the pellet. So typically what we do is we have a bunch of sensors and cables and PLCs and all sorts of fancy things to know the orientation of the pellet. Using a webcam, which costs $1,000, a little Raspberry Pi, which costs $3,000, I'm now able to virtualize and determine the orientation of the pellet. So watch the video. So it says OR1, and then the operator turns the pellet around and it says OR2. That's a simple classification of now I've removed all of the hardware, all of the PLC code on the production line by simply using an AI classification to determine the orientation of the pellet. It's a tenth of the price of what it would have been. So technology doesn't have to cost more. In fact, we can use technology to reduce the cost of components. The next example is what's very critical. You definitely don't want to buy a BMW with this, what we call a link arm. And you can see it's a banana shape. You don't want the banana shape the other way around. So this is detecting that it's in the correct position. When it's in the correct position, we allow the operator to switch on the tightening tool to tighten the bolt. If it's in the wrong position, the camera tells the bolting tool it's in the wrong position. Do not switch the bolting tool on. And that's how we can control now what was previously not possible, the orientation of that link arm. It changes the dynamics of your vehicle. So here you see, again in the video, when the operator turns it around, the other link arm is in the wrong position, and we basically say other, and when it's other, we don't allow the bolting tool to switch on, so the operator can't make a mistake. So this is an example of how we actually use technology to reduce the skills required by an operator to make effective quality components. And I think this concept of technology requiring more skills on the shop floor is a misnomer. Technology should be reducing the skills barrier so more people can enter into the workplace without skills. And technology should be enabling those people to work effectively. Another example, another kind of AI that is used is quality inspection. I think this is the most common one. And I will quickly breeze through this, but this is just an example of a very difficult component to inspect. So this is a camshaft of an engine, and you have these small imperfections on a camshaft that need to be detected. And only very trained operators that have got years and years of experience of identifying these little blemishes on these precision surfaces are able to detect these faults. Now, as a company, a US-based company, that's now created a model that can actually detect these blemishes inside these very critical components that obviously go into an engine. Another use case of computer vision AI for quality inspection. So I'll quickly show you the next couple of examples. I'll get through the animations. So this is an example of a quality inspection of a bolt. So you want to check the integrity of the coating of a bolt and obviously the machining. And this is a classification model that's able to tell you quality inspection of every bolt. Now you try to imagine a person inspecting every single bolt coming out of a machine becomes very, very difficult. But now using AI, and because the systems are getting faster and faster, we're able to achieve that. Probably the most interesting part of computer vision that I think is the most interesting is this concept of, or this idea called object detection. So how can we use computer vision to detect objects in 3D space? So think of a self-driving car. There are a bunch of cameras, and they're able to detect objects, classify what object it is, classify where the object is, and make a decision. Do I run Andre over? I'm using Andre because I know him. Or do I avoid Andre? So these are the object detection models that are running in self-driving cars. But how can we use that concept on the shop floor? So this is an example of an object detection from a concept perspective. So we have an input image or a video. Could be we have some clever stuff. And again, the clever stuff I put in these boxes because I don't understand what's going on in the box. And the output of that is what we call a classification model. So I'm able to create a model that can determine it's a dog, and the coordinates of the position of the dog, a person, and a bicycle. And these are the coordinates. So I know in 3D space on a video exactly what the live coordinates are of an object. Doesn't matter what the object is. So here's an example where, in this case, it's out of scene at the moment. The object that we're tracking is actually a bolting tool. And before I play the video, I'll explain to you why it's so important, is that You see these 4 bolts that are tightened. This is, again, BMW X3. The sequence in which we tighten those bolts are important, because you guys know on your wheel, you never tighten in a circle, you tighten zigzag. So there are many components in a car that need to be tightened in a certain pattern. And so how do you ensure that that pattern is adhered to? Only when the bolting tool comes into the right region of interest, as we call it, do we switch the bolting tool on. So the operator can't pull the bolting tool trigger unless it's in the right position, and you'll see that now. So she brings it into position, she takes it to the first position. You can see the 3 dots are the key points of that object, the socket, and only when it's in the right position do we switch it on. Again, here what we're doing is we're now reducing the skills for a person to perform this operation. We're not increasing the skills to use the technology. Technology is actually lowering the barrier to entry for people to get jobs. So this notion that AI is going to take jobs away, I think is the complete, it can in some cases, but I think in many cases it can actually create opportunities for people. Here's another similar example in the same factory where we're now checking the position of the bolting tool, and you can see there's basically 7 positions the tool needs to be in, and the operator needs to remember the exact sequence. And if you do this 8 hours a day, it's very easy for you to make a mistake. And now the AI is actually tracking the position of the bolting tool, and if it's in the wrong position, we flash a red light to say go to position 1 or 2 or whatever that is. So it's exactly the same concept. This is an example of tracking the hand. So this particular example is a video of me going into a bin to pick the right component. So if my hand goes in the wrong bin, it switches and tells the operator wrong bin. So now I can actually track the position of the hand to ensure that I'm picking the right components from a part bin, for example. And probably one of my coolest ones that I really enjoy is to replace various components on a factory. So here, what I'm simulating is a push button. You'll see it in the video. So I have a sticker, which costs all of a few cents. And using the same AI model, I'm now able to put my finger on the sticker and simulate a physical push button. So now I'm virtualizing physical devices, and I don't need those physical devices, because a safety, you walk outside here and you find all of the push buttons. They cost you, to get a push button to work inside a factory will cost you 10K before you start. So now I've virtualized that, and what that means is I can actually then make 50 push buttons if I want. I can have a push button for the left-hand operator, a push button for the right-hand operator, or I can make any number of these virtualized devices because it's software. And that's the opportunity with AI. So this idea that the stations are going to get more expensive is completely incorrect. I think the stations get cheaper and much more flexible using AI. So that's computer vision. Just looking at my time. Okay. I'm going to breeze through the big data as quick as I can, but there's 2 sections within big data. The one is predict and the other one is prescribe. So on the big data side, there's a couple of examples I want to share with you. The one is the most common one. So predictive maintenance has been a hype for a long time, and everyone talks about predictive maintenance, but basically conceptually what it is that you have, in this case, it's a vibration profile of a machine. So think of your pool pump, think of your fridge at home, think of your aircon at home. When you walk past that fridge and it's sounding funny, it's vibrating differently, which means that there's a problem. And simply put, the vibration sensor is now detecting that, and it's able to predict with some clever stuff in the background what it's going to look like into the future, so that you can proactively call the person out to come and fix your fridge. And that's what you do on any vibrating asset. And these are very simple models. The hard part about vibration is actually sampling the vibration at the right speed, which is not an AI problem, not a technology problem. You can walk outside here, I'm pretty sure you can find high precision vibration sensors, and that's not going to be a problem. But it's a very simple concept. A lot of hype around predictive maintenance, but it's not a very complex concept. So you just think of your fridge and you walk past and you hear it different, you know that there's a problem. What is interesting is this another concept called autoencoders. And you can just replace the word autoencoder with the concept of anomaly detection. So how do I detect for anomalies? So an autoencoder concept is very simple. So again, this is a slightly technical, but bear with me. So imagine I input a picture of a cat. An autoencoder is basically zip files. You guys know zip files. So we basically shrink that image down as much as possible, many images down as much as possible to the smallest possible size. And then I have a decoder that would decode that image to try and replicate the image. And what I do is I compare the input image with the output image, and the difference tells me my error. And so if I can determine how much error I want to accept, and then if the error is too much, I can put more images in and train the model. And so what I can then do is I can put another picture of a cat in, and then see what the output is, and it's still a cat, and that for me that error is still acceptable. But if I put a dog into that autoencoder, I get something weird out. I don't know what creature this is, but it's a mixture of a dog and a cat. And then when I compare the input and the output, the error is much bigger. So that's an anomaly I've detected. So if I'm looking at a certain position, like I want to check Brandon's position, he always needs to be in this position. And the moment he moves, I can now use an autoencoder to determine if he's now no longer in position. So that's an anomaly detected. And we can use this in multiple ways inside a factory. This is just an example of images of dogs and cats. So how have we used it? So here's me on one of our production lines, and I'm fitting in a set of bearings that get pressed into a differential. Differential is obviously a key part of the car. And what you'll see over here, I'm loading the differential, and what's very important is that we monitor the force and displacement of the bearing. And basically what happens is when you start the machine, there's a force displacement that we monitor. Comes in a second. So basically as you press the bearing in, the displacement goes up, the force goes up, and you have this thing. This is where it makes contact, and then it needs to rise up like this. And what we do is we put these evaluation windows. And so this force and displacement curve needs to go through these evaluation windows. And if it does that, we know we're good. And this is the way we've been controlling production lines for 20, 30, 40 years now. And what happens is if there's ever a situation where the force displacement curve goes out of the window, we fail the part. But what happens is when this fails, it's too late. The part's bad, you stop the line, and now what? Now you go through this fault-finding process. So is there a way we could use this data we've got to help us predict when a machine's going to fail? So yes, we can. So you do this with basically an autoencoder. We feed in hundreds and hundreds of graphs into an autoencoder. We get the ideal graph out of that. And what I can then do is I can then input that graph into the autoencoder, and I can actually determine these different errors. So in other words, the difference from the ideal versus the actual. And the size of the area between the graph tells me how big my error is. And I can then basically do some simple evaluation on that and say, okay, if I have errors above a certain size, and if I have 5 of them in a row, I want to flag and stop the line. But bearing in mind, these parts are still okay. They're not bad parts, but I'm now predicting that there's an error on its way or a failure on its way. So this is an example of how we can use autoencoders for predictive maintenance on machines. And then another example, this was an unfortunate situation that happened to us. This is a gauging machine that we've delivered to a customer. And basically, you see the measurements that come out of the machine are within those bands. And just to give you some context, this band is 50 microns. So 0.05 millimeters. It's tiny. And that's the range that we're trying to measure. And what happened was one of the components in the machine had a burr from the machining center. It knocked one of the sensors. And now we started measuring incorrectly. But it was still within range. So it didn't fail. So it was still a good part, according to the machine. But we were measuring incorrectly because the sensor got bumped. If we had an autoencoder in retrospect, we would have picked up this problem much sooner. So it's another example of how we can use AI to predict and help us prevent problems going into the future. I'm going to quickly get through because I'm getting flagged at the back over there. So prescriptive is I'm going to get through this one quite quickly, is a very simple concept, is where you have a machine, you have a lot of output data that goes through that. I have some input data that goes into a control system or PLC or whatever that is. And then I have a brain, an AI model that's now inputting, getting all of the data of what was put into the machine, all the data that's come out of the machine, whether it be quality, speed, whatever that might be. And then I can create a brain that basically sets more optimized parameters to the control system to improve for quality, to improve for output, or whatever that might be. And that's basically what a prescriptive model is. And what I can tell you is, I'm going to breeze through these slides quite quickly. We've tried this ourselves and failed horribly. This is an extremely difficult thing to get right on a live production line, to have prescriptive models where we try to do this on one particular application to improve the output of a production line of a differential, to select the right thickness of a shim. And we've basically only went from 70 to 80% first time through. And the message I want to leave with you here, this is where the hype gets too hyped. There's a reality to try to get these models to run live on a production line. It's not that easy. If you're interested, there is one company in Cape Town called Atlantis Foundries that has really done it well. In a foundry, it's really amazing. I actually have a podcast, and I had the MD, Peter Duplessis, on the podcast, and he talks really elegantly about how they've gone through a mindset shift change to actually implement prescriptive AI using a company called Data Profit. So check for Disrupted Factory podcast on YouTube, and you'll see his whole interview. I'm going to skip the large language models because I'm pretty sure between today and tomorrow there'll be lots of chatbots and ChatGPT stuff. But what I did want to share with you is something new that is happening. So we had this robot on display 2 years ago at this show. We don't have it here this year. But basically, this is me playing noughts and crosses against a robot, right? So just for disclaimer purposes, I let it win. But it's played probably 20,000 games. It never lost. It's had lots of draws, but it's never ever lost against a human. And the idea here is, imagine I played this for 8 hours non-stop against the robot. Eventually, I would lose a game because there's no ways that as a human you can be repeatable in this. And basically, conceptually, this is a very interesting opportunity that we've got here. So let me show you how we put that together. So the first thing is, obviously, there's a robot. It's collaborative. There's a vision system that was actually checking the X's and O's. Then there's another brain which you don't see behind there. So this is the brain playing the game against me. So this is the AI model that is actually trying to beat the human. So it's now obviously trying to beat me. So fortunately, it's just noughts and crosses. But you can program the model to try to achieve a certain outcome. And now there's physical things. It can see. It's got some physical actions. And then there's a human that's obviously part of this whole story. That's me. So these are the 4 elements that we put together to form the system that a human and a machine can interact intelligently together. Because it's playing against me. It's trying to beat me, and I'm trying to beat it. But let's aggregate that out into a much broader concept. And there's a new buzzword that lots of the consultants are talking about called agentic AI. So the idea of an agentic AI is basically autonomous decision making. So this brain is making decisions autonomously of me. I've not given it any input. We've programmed it to make decisions against me. So let's aggregate that out to a production line, a whole production line, not just one machine. So we have a big production line, and we have lots of little AIs. And all of the slides I've shared with you up until now, I would term as little AIs. The computer vision, the prediction, all of those things are little AIs that we can plot on a production line. But what doesn't exist yet, but is definitely on the way, is the whole big brain of the production line. So what do you want to optimize for quality, for throughput, for whatever that is? So I call that the supply chain optimization agent. This is the thing that we need to train on what we want out of the system. And the scary part out of this, because at the moment, if you want more output, it's a human that gets involved. I want to produce more, switch the line faster, put more operators on the line, whatever that might be. So there's still humans that make that decision. But if we get this model right, the human becomes a much smaller part of this production process. That's why I put the human in gray over here. And with that, I'll end off with, again, a selfish plug for my socials. So follow me on LinkedIn. I make a video every Monday with lots of this stuff I talk about. I'm pretty passionate about it. And join me tomorrow where I talk about how we're using this technology to change people's behaviors on the shop floor. Thank you.